So in this video, we'll explain about the Lamé equation. Okay. So Lamé equation is mainly related to the thick cylinder here, and the equation contains the what are the different types of the stresses developed inside the cylinder, and related in terms of equations here, like pressures and such. As we previous video we discussed that in thick cylinder there are mainly three types of the stresses developed. Okay, inside the cylinder. One is the circumferential stress along the diameter, one is longitudinal stress along the length, and one more is radial stress. Okay, this is one of the additional stress it is developed in the thick cylinder because of the wall thickness is more, but that is radial stress is absent in case of the thin cylinders here. Okay, these three we club together and we will form a equation here. Okay, first if you see that picture A, the figure A, it is a thick cylinder. Okay, thick cylinder, just leave it this shaded area and just black one circle and outer one circle, consider that. Consider a thick cylinder of the outer radius is R0 and inner radius Ri. Okay, and its inside fluid pressure is P. Okay, and its length of the thick cylinder is L. Okay, we'll start with the thick cylinder here. Okay, consider thick cylinder as shown in figure A. Okay, so let Ri and R0 be the internal and external radii. Okay, radii of the cylinder. Let P equal to the internal fluid pressure L equal to length of the cylinder. Next, we will consider a small elemental ring. Okay, so we will derive on the basis of the ring, then we will integrate the with respect to the inner to outer radius. We will get some equations here. I considered one of the elemental ring here. So the elemental ring is at a distance of x, and with a thickness of dx. Okay, so its thickness is dx, as you can see here, and it is at a distance of x from the center. And at the inner wall of the elemental ring is the fluid pressure is Px, and the outer wall of the ring is the fluid pressure is Px plus dpx. Okay, so next we will consider a small if you see the figure B, it is a semicircular ring we are considered here. It is at a distance of x from the center, and dx is the thickness. Okay, and the fluid pressure at the inner wall of the elemental ring is Px. It is Px. Here it is P of x, and outer wall of the ring is Px plus d of Px. Okay, so consider an elemental ring. Consider a semicircular elemental ring at a distance of x, with x from the center, with thickness, what is the thickness? Dx, with thickness dx as shown in figure B. Let P of x equal to the fluid pressure at inner wall of the elemental ring, right? As inner wall of elemental ring, okay, elemental ring, and P of x plus d of px. d of px equal to the fluid pressure at outside, at outer wall of the ring, outer wall of ring. Okay, so it is in opposite direction, outer wall of the ring here. So mainly here, same by considering the elemental ring, you have two types of the forces it will be developed here. One is bursting force, one is resistance force here. Okay, so bursting force, just elemental ring is subjected to two types of the forces. Okay, one is the bursting force FB. First one is bursting force FB due to radial pressure Px, due to radial pressure Px and Px plus dx, due to radial pressure Px and Px plus dx, Px and Px plus Pdx, P of dx, due to Px plus P of dx, acting on areas which areas Px is acting in which area? In this area. In this area means x plus x, x plus x, it is 2x along the length, 2x into L, right? 2xl, x plus x, it is 2x along the length, it is 2xl, that is 2xl. Px is acting in 2xl area and areas, and Px plus Pdx, where it will be acting here? Px plus Pdx, it is acting at here x plus dx, right? Here in this area, outer area, x plus dx into 2 times into L along the length here, that is x plus dx into 2 times, right? Into 2 times along the length here. This is the area for this pressure, and 2xl is area for the Px. Okay, this is one bursting force. Again, the resistance force. The resistance force acting that is sigma r Fr, resistance force acting Fr equal to how much you get? That is the resistance circumferential stress. It is acting that circumferential stress along with this the rectangle area. How much this one here? This is the dx, right? It is the dx. This is dx, this is dx. 2dx into L along the length. That is into area is 2 times dx along the length here. Along the length. This is how first you have to differentiate the areas. Areas are very important. If you consider the bursting force, pressure will be main point. If you consider the resistance force, circumferential stress will be main point here. But areas you have to consider this internally this area, externally this area, and the resistance is only this, the whatever the rectangular projected rectangular areas 2 times. Okay, so now we will first write the bursting force, these two types of the forces acting here. Therefore bursting force, first bursting force, therefore bursting force equal to FB equal to, first we will consider the inner, that is Px of the ring. We are only deriving everything related to the elemental ring, right? Px, this is the pressure, into area is how much? Into area is x plus x. This is 2x along the length, right? Into length into, that is 2x into L. This is bursting force plus and minus, this is the one more force. Okay, the one more bursting force, it is acting here. Pressure is how much? Px plus P of dx. P of dx, pressure. And how about the area here? Area is x plus dx. This is x plus dx, here x plus dx. 2 times x plus dx, that is x plus dx 2 times along the length into length. This is the area. This is the area. Bursting force. Now the resistance force equal to F R equal to, see here, this is the circumferential stress, it is acting along the circumference. This is the area in which, so circumferential stress into, what is the area? Only this much you have to consider. How much is the thickness here? Dx. Dx plus dx, 2 dx, right? That is 2 dx along the length. Okay, along the length here. This is the resistance force. Now for equilibrium, Fb equal to Fr, right? That is Fb equal to Fr. Now equate this, will be equal to this here. That is, this time equating here. Left side, Px into 2 times x into L minus Px plus P of dpx, okay, minus 2xl, that is into 2xl plus 2 dx into L, 2 dx into L, right? This is bursting force equal to resistance force. Resistance force is sigma c into 2 dx into L here. Okay, so px into 2 times xl minus px plus 2p px plus p into dx. Next 2xl, that is 2xl plus 2 times dx into L here. Okay, now just simplify here. This will be equal to px into 2xl minus px into, just multiply, px into 2xl, next minus px into 2 dx into L, right? Next, so minus p into dpx into 2xl minus p into dpx into 2 dx into L, right? Just I multiplied here. Now the this and this will be cancelled here, and so neglecting the higher order terms here, that is neglecting higher order terms, which is the higher order term here in this dpx and dx, right? Dpx and dx here, that is p into dpx that is p into dpx into 2 into dx into L. This you have to neglect here. You have to neglect. So what is the remaining here? This will be equal to here sigma c. This sigma c into 2 times d into xl, right side, right? That is the resistance force here. Now the what remaining here, that is minus px into 2 times dx into L minus p minus, this is px minus px into dpx into 2xl. Anything else left side? No, nothing, everything. This is neglected. Equal to sigma c into 2 times d into dx into L here. Okay. Now again further simplify. How much we'll get here? That is minus 2 minus 2 minus 2 px into dx into L equal to again the this 2 cancels, L and L cancels here. Okay, the finally the remaining terms are, we will get here minus px, right, minus px into dx that is minus x into dx, that is minus x into dx x into dx equal to sigma c into dx. Just check it, this one here. You will after simplification you will get finally this equation here, this equation. Okay, minus sigma c into dx. Just check it, this one. You will get the final like this here. Okay, so now the just sigma c into dx equal to how much we will get here? That is plus sigma c plus, we'll make it this one as 0 here, that is sigma c into dx plus px into dx plus x into dx equal to 0, right, equal to 0. Now just divide by dx here, that is sigma c plus px into dx, this is dpx, right, sigma c into dx plus px into dx plus x into d of px. This is d of px, this is d of px, this is d of px equal to 0 here. Okay, so now after simplification, sigma c plus px into px plus x into d of px by dx equal to 0. Okay, this is one equation. This is one equation. You just simplify for you will get finally this equation here. Okay, maybe here little bit while solving it may be mistake, but if you simplify correctly you will get this equation. Call this one as equation number 1 here. Okay, this is equation number 1. Now along with the radial pressure and circumferential stress, now we are equated and we got this equation. Along with these two, one more the stress it will be acting here, that is longitudinal stress. Okay, along the length of the cylinder. Okay, also an element is subjected to longitudinal stress. Longitudinal stress along with circumferential and radial stress. Radial stress. It means one more stress is the longitudinal stress, also it is subjected here. This is one equation. Now we will write the circumferential strain or if it is subjected to longitudinal stress, the longitudinal strain will be developed here. Okay, therefore, so what is the longitudinal strain? We will write here. How we will write the longitudinal strain here? The longitudinal strain, therefore, longitudinal strain equal to longitudinal stress divided by E, right, minus and apply the Hooke's law, minus nu into circumferential stress divided by E minus one more radial pressure, it is acting here, right? Nu into radial pressure divided by E. This is also one more. But this radial pressure is, one is circumferential stress and radial pressure it is in opposite direction. Okay, this one is the minus here. So therefore longitudinal stress strain equal to sigma L by E minus nu by E minus, take it nu by E here, nu by E outside. How much we'll get here? That is sigma C minus the Px. Sigma C minus Px here. This is the longitudinal strain we have developed here. So the condition for the thick cylinder is the longitudinal stress, the longitudinal stress or strain remains constant throughout the length here. Okay, whatever the stress developed inside the longitudinal stress developed inside the cylinder is throughout the, it is same throughout the cylinder here. That condition we have to apply here. Okay, so longitudinal stress, so as per the Lame's law, according to Lame's equation, longitudinal stress strain or longitudinal strain is same, is constant, is same throughout the length. Throughout the length. This is one condition as per the Lame's equation here. Okay, so if this is the equation 2, just call it as equation number 2 here. So from equation 2, so longitudinal strain, if from this equation, if longitudinal strain remains constant, to be constant, then sigma C minus Px should be constant. Then only the longitudinal strain it will be constant throughout the length here. Okay, from equation, if stress is constant, if longitudinal stress is constant, the term sigma C minus Px should be constant. Okay, so I write this should be for equilibrium. It means for the longitudinal strain remains constant, you should make this should be constant. Therefore sigma C minus Px equal to 2a. That should be 2a. Just 2a is where 2a is constant. Where 2a equal to constant. Okay. Now substitute this equation 3. That is, this will be equation 3. Call this one as 3. Okay. Now substitute this equation 3 in equation 1 as we derived sigma C. Just open that one, equation 1. Substitute equation 3 in 1. I noted down the equation 1. Okay. So what is the equation 1 here? That is the equation 1 already we noted. Just I'll substitute that one here. That is Px plus 2a. Just make it this one as sigma C equal to Px plus 2a. Okay. This is 3. Equation number 3. Now substitute the circumferential stress value in equation 1. How the equation 1 is? That is Px plus 2a plus Px plus x into d of Px by dx equal to 0. As equation 1 is, what is that? That is sigma c plus, what is that? Px plus x into d of px divided by dx equal to 0. This is equation 1, right? Now substituting the sigma c value, this sigma c value here, only I replaced. Okay, this is the equation here. That is x into, now just simplify, this will be x into d of px by dx, this is one term, equal to minus 2a, that is minus 2, this is px 2px and plus 2a. I will take this one here, the minus 2 into px plus c. Directly I simplified here, right? This is px plus px 2px plus 2a I taken in the right side here, that is equal to okay, just I take it the equal to 0, this I took it in the right side here. Now further simplify here x into d of px and dx equal to minus 2 into px plus a here. Now separate the variables and integrate. This is one equation. Separate the variables and integrate. Okay, how you will separate here? You have to separate the variables. D of px divided by px plus a. Okay, px plus a equal to minus 2 into dx by x. See here, just I took here d of px divided by p of x plus c. P of x plus a equal to minus 2 into, that is dx divided by x here. Just I separated the variables. Okay. Now I will integrate here. This is integration and this should be integration here, and integrate. How we will get this? Because px, this is the px here. Px with respect to px and dx with respect to x here. Okay. This is the integration. Now what we will get here from this one? Log to the base e, right? Log to the base e px plus a, right? Px plus a. Px plus a equal to minus 2 into, equal to minus 2 into log to the base e, right? Log to the base e x. Log to the base e x plus c, where c is the integration constant, right? What is the c here? We'll just further here. What is the c? C is integration constant, where c is integration constant which can be written as another constant b as log to the base e b. We can replace c, it is integration constant, that can be written as b as log to the base e b. This is also constant only. Okay, so now what is the how the equation looks like here? That is log to the, therefore log to the base e px plus a equal to minus 2 into log to the base e into x plus log to the base e b. Log to the base e b here. Okay. This how we will get here, that just this will be equal to log to the base e b minus log of to the base e x square. Can I write it x square here? This is log to the base e px plus a. Okay, So again further simplify, how much we'll get here? Log of a minus b is log of a by b. That is log to the base e b by x square, right? B by x square. I can write this one as b by x square. In the left side, log to the base e px plus a. Okay, and therefore from left and right side, what we will get here? So just remove the log to the base e. Therefore, how we'll get after simplification? Px plus a equal to b by x square. B by x square. Therefore, px equal to a plus b by x square minus a. B by x square minus a. This is one equation here of the Lamé equation. Call it as this one as equation number 4. Now substitute equation 4 in equation 3. In 3. What is the equation 3? You just check it. The equation 3 related to what? Sigma c. Equation 3 is this circumferential stress. Sigma c equal to px plus 2a. This is equation 3, right? Before I given this equation as equation 3. Now substitute px value in this equation. This is third equation. Now substituting here. That is b by x square equal to px plus 2a. Right? B by x square equal to px plus 2a. Therefore, no, sorry, px we are substituting, right? The sigma c equal to b by x square plus 2a, right? This is the circumferential stress. So this is one important equation, this is one important equation. So px, one is px equal to b by x square minus a, this is one equation, and circumferential stress equal to b by x square plus a. B by x square plus a. Okay, just check it. The final equation is you will get b by x square plus a after simplification. This is a here, sigma c. This is plus a. Where a and b, what are the a and b? Where a and b are the constants, where a and b are the constants, a and b are the constants, depends upon boundary condition. While solving the problem, apply the boundary condition and try to solve the values of a and b, a and b here. That is a and b. Okay. Constants depends on boundary condition. Boundary conditions. Okay. X is the radial distance. What is the x? A and b are the constants, and x is the radial distance. What is radial distance? From the center. From the center to the wall thickness, to the wall where stress is to be determined, right? Where stress to be determined. To be determined here. Okay. So this is called Lamé's equation. These two equations are called Lamé's equation here. Okay. One is px equal to b by x square minus a, and circumferential stress sigma c equal to b by x square plus a here. In the problem, he is given the conditions. Apply the conditions and try to find out the constants a and b. Okay. And where you want the stresses, you can find out at a distance of x here. Okay, this is how you have to derive the Lamé equation. Okay.